So my name is Jarno Vanne, and I'm an associate professor from Tampere University, Finland. And I can see here a few familiar faces too, but there are also some new faces for those who haven't met me before. Just to tell you that this is not by far my first time here, so I have spent at INSA back then around, let's say, 2 to 3 months altogether. I don't even remember how many times I've been here, but let's say that this is at least my 5th or 6th visit here. Okay, here you can see Ultra Video Group, which is a research group created by me around 10 years ago. And actually this picture was taken before this COVID pandemic started, so there are some changes in personnel, but more or less the size of the group is like this, a little bit smaller nowadays. And today I'm very happy that there is also one other member from our Ultra Video group here, Alex, who has become one of the cornerstones of our group nowadays. So this is a great thing to have you, Alex, here too. Before I start really this presentation, I'd like to ask one question: that how many of you is working on video related topics? Great. Almost all. It's good to hear, and hopefully the remaining ones are at least interested in hearing about these things. Okay, then another question here: how many of you have heard about Ultra Video before? Okay, good. Then, but maybe there are also some participants on the line who haven't heard about it, and probably that's why I thought that maybe it's good to give a short recap of our group first, and then talk about our main research themes nowadays. It goes without saying that video coding is still the main thing what we are doing, but as the group size has become bigger, also the area of interest has increased. And when we think of video coding, typically video coding itself is not enough, but typically there are also some processing around it which is needed. And on the other hand, if someone starts thinking that why are we compressing video, typically for storage or transmission, that's are quite typical like applications for it. And that's why we have also extended our expertise field to video streaming. And here in this presentation, so I will first start with these 3 items, and then I'm going to show you some like concrete real life applications where we have applied and deployed these techniques and technologies. So let's start with this group intro first. So currently, I already mentioned something about this basics. So there are around 15 guys at the moment in the group, and basically the knowledge behind it has existed already more than 20 years. So these activities have been started in the early 2000s, but the group itself has been founded in 2011. And currently, I would say that our group has established its position as the #1 academic video group in Finland. And I'm not talking about any more video coding group. I would also call it like video group, because there is more to it than just this video coding itself. Again, the same group picture, and now when we have finally got rid of different COVID restrictions, we are going to take a new picture where all the new members are also present. And then about collaboration in general, nowadays we are working in many different EU level projects, not actual Horizon or those new horizon projects, but more like in Excel and KDT type initiatives. And here you can see a list of some of our biggest projects in the, let's say, during last 10 years, and one could also find one quite good acronym, quite familiar acronym, 4K references. We're also in some of one of the partners. But nowadays, if we are talking about our ongoing projects, there are only two here currently listed, New Control and Mercat. They are those Excel projects. And besides these, we have a quite big number of different national projects nowadays. So I'm also happy to have this kind of collaboration, which wasn't so easy to achieve, let's say, 4 or 5 years ago yet, but now there is also quite strong national initiatives in Finland. And if you like to know more about our group in general, just visit our website or on our GitHub site. I would say that our GitHub site has increased in size quite a lot recently, and it starts looking like a real, this kind of collection of different multimedia tools. And about those tools, I'm going to talk today, at least those basics. And by the way, if you have any questions, feel free to interrupt me anytime you like, so that this talk could be more like an interactive talk, not just like that I'm talking and you are listening. So that's typically the most fruitful way to organize these. Okay, let's start then with our ambition. So if I have to somehow describe what is our main focus, I would put it in that way currently. So we are developing different dedicated video coding solutions for different media applications. And the range of platforms is pretty wide nowadays. We have done some experiments in Raspberry Pi, but of course, multi and many core processors and FPGAs are the most frequently used platforms, but also we have done something with GPUs, especially nowadays when talking about machine learning and those different technologies there. But also we have worked with cloud encoding. So I would say that this range is pretty wide nowadays. And if we think of a typical assignment, what kind of research activities we typically carry out? I would say that there are basically two different options, and I believe that especially I believe that these both are pretty familiar. You are pretty familiar with them. So the first one is like that there is a protocol or some standard or something, and you may also find a reference implementation for it. But the problem is that it's not fast enough, or it consumes too much power, or whatever can be, maybe the latency values are not adequate enough, or something like that. So basically that's the first thing, that we try to optimize existing solutions. We don't develop those algorithms itself, but those existing algorithms we try to implement, for example, on embedded platforms as efficiently as possible. And the other assignment can be that, for example, some company contacts us and say that this is a nice protocol and it works fine and we have a nice implementation for it, but unfortunately some specific feature is missing. So first what we do, we just implement that feature and try to also optimize it so that the company is also happy after this optimization. And when adding the new feature there. And about the main research question, it's quite simply to put it here. So we are dealing with this problem that we have three different dimensions in here. It's quality, bit rate, and complexity. And I think this all of you who have worked with video know this very well, that this kind of trade-off we always have to make. And I would say that there aren't many situations where you can say that all of those are free. Typically, at least one of those aspects is always a little bit at least orange or red. And that is the dilemma what I have tried to solve for the last 20 years, but still I'm struggling with it. So hopefully someday we are able to find that silver bullet which basically solves all those problems there. Okay. And then about our key areas, a bit more carefully in that sense. So video coding, and here you can see just a sneak peek of everything. I'm going to touch some of those in more detail in the following slides, but just to give you some kind of an overview what kind of applications we are currently dealing with. But video coding is by far the biggest thing still. But as I already explained, also this video processing part has increased recently, and also this video stream. So these three things: coding, processing, and streaming. And we are not just developing those techniques, but we also like to have some applications for them. And here you can see the list currently. And this is like just like, it's not anyhow a precise list of what we are doing, but this is just like samples of things what we are doing. And one thing which can be easily seen here is that quite many of these are more or less related to autonomous driving and transportation, because our recent projects are very much about those. Volumetric communication here. Unfortunately, I didn't take any examples of that, but basically what we mean here, that if you think traditional Zoom meeting like this with video, it's like 3D conversation and collaboration. But with this volumetric communication, I mean that first we have to create like a point cloud of a person, and then make it feel like that you really meet the person, like in-person communication, that if there is not that like, let's say, this kind of network in between. So we try to make it as realistic as possible, but this is something that is at its very early stage currently. But actually there is a big national project what we are currently applying for, and that is mostly related to that project, and that is a very interesting approach, and that would be also one nice way to collaborate, for example, with INSA, because also in that project we are mainly focusing on using these traditional video coding standards or their derivatives for compressing those point clouds. And when we compress something, we also have to decompress them at some point, and then probably I could turn my eyes on you, and probably if you happen to have something on that side, probably that would be nice way to establish some new branches of collaboration. Any other questions at this point? Okay, I heard something, but probably it wasn't anything related to questions. Okay, then let's look at our research teams then more carefully. So let's start with video coding for humans. Unfortunately, my title is not completely visible, but I hope that at least you can see it on your own computer. So video coding for humans, I think that is the most traditional approach for video coding in general, and that's still our main focus when talking about video coding. And this is something that I believe that most of you have heard during the years that we have been developing. This was our open source VVC encoder. And when we started this project, I think that our objective was pretty ambitious, and we also heard quite many skeptical comments about it, that why do you have to start developing your own encoder, because there is also X265, etc. And some kind of comments that most probably that project won't see its first year birthday or so, but we are still alive and kicking with this one, and I would say that we have been quite successful with it. We started in that sense, even though the target was pretty ambitious, we still started our work quite carefully, and we tried to just make something working first, and then we have like I would say that appetite has been increasing with eating, and let's say the first milestone we were able to achieve was this open source competition award in 2016. This project was started already in 2012, but the research group was really small back then, so there weren't many developers. So I would say that the pace of development wasn't very fast. But when we were able to start increasing the size of the group, also we got more power for the development. And at this point, we were mostly developing Quasar at intra-encoder level. But when we increased the size of the group, we were also able to start focusing on inter part of the encoder. And then in 2020, we were again able to publish new version of Quasar called Quasar 2.0, and that also won one competition in ACMM's conference. And actually, I would say that the latest version of Quasar is, I would say that it's already pretty efficient, and we haven't marketed it so much now, but currently I would say that it's quite competitive. And when we won this competition, or already before that, we removed this word, this intra word from there, because now we are not we're talking about open source intra encoder, but also whole HEVC encoder. And since then we have applied it in many different platforms, but it has also been adopted to many different frameworks. Of course, FFmpeg and LibAV, but there are also some other quite interesting things. For example, Quasar is used as like a benchmark software in this open benchmarking software set. And still, if we look, this diagram is taken from, I took it like last week, and you can see that quite many viewers and visitors are still around Quasar. And if you think that during the last 2 weeks there has been like, let me check the number, I cannot see it very well, but something like more than 100 unique visitors there. So still, so I would say that it is still gaining traction quite nicely. And that's why when we think of its latest performance figures, etc., we have already removed also this word academic here, because I would say that in some, if you select specific encoding parameters, we can call Quasar nowadays already #1 open source HEVC encoder. But of course, it's always dependent on the parameters we are using. But there are some configurations where we are able to beat, for example, X265. And currently, actually, because the development was started in 2012, we are currently celebrating Quasar's 10 years birthday. But when we think like this kind of, yes, please.
Do you plan to remove also the open source word or not?
No. Probably we are going to keep that one. But this one is a little bit trickier word in that sense, because I was just starting to talk about this kind of idea that if we have like this kind of Quasar somewhere in the space, and sometimes something can also break away from it. That something just like when talking about company language, something can spin off from that. And in our case, it means that if Quasar is here, something new has been already broken away from there. So our latest encoder is called uvg266, and this UVG stands for Ultra Video Group. But because Alex is going to talk more about that, I'm not going to spoil your presentation and continue this. But this is something, when you asked me about this wording here, this HEVC, of course, we are going to have this, I would say, forever with VAADER, but in that sense that we are not anymore dealing with HEVC so much. So one could also think that there could be also the word VVC, but we wanted to have completely different names with VAADER and this new encoder, even though this uvg266 is built on VAADER. So there are lots of same techniques used there. Okay, that was basically all about conventional video coding for humans. And this is just like a short recap of if we think what does it mean when we are talking about conventional video coding. So basically we have raw video, what we have just captured there, and what we are doing with it. We first encode it, then we transmit it, and then we decode it for playback. And typically we just rely on that okay, we know that that standard works fine and it's able to compress the video as well as possible. But especially personally, I have started to think that probably we should also more carefully think that what we could do with this kind of idea that there are like this quality bitrate complexity problem, and if we just use that basic standard for that and do nothing and just somehow hope that we are able to solve this problem. And that's why I have started to talk more about this kind of idea that we need more content awareness for video coding also. And what it means in practice, it means that we are not just thinking that this is like homogeneous, let's say that the whole video is not just like a homogeneous entity, but there are areas which are of more interest to someone, and then there is like this background which is not so interesting. And for that, we'd like to use some kind of AI-based solution in order to find this region of interest in this video. That somewhere, most of us know that there is something more interesting in the video than, for example, some background issues over here. Of course, it depends on the situation. For example, I would say that the first impression would be that okay, maybe this is the most interesting part of the video, that how those coffee bags are moving there. But there could be also some machine user here, and suddenly this part would be the most important part when we are detecting what the machine user is, for example, how he or she is using the machine. Anyway, we need for this kind of, let's think that this is the region of interest. Now we need some kind of region of interest mask for it in order to know that this area we should encode with better quality, and the remaining parts we can just keep with much less quality, so that we are able to save some bits and to somehow achieve more economic compression. So this is the first part of the story, that okay, let's encode this with better quality, and these areas are very lower quality. And when one is thinking of how much we can save, I would say that the rule of thumb is that this high quality area costs as it would cost without doing this, and these low quality areas come almost for free. So in that sense, at least, I would say that half of the bits can be saved by doing this, compared to the situation where everything is encoded with high quality. Okay, that was the first part of this kind of a more intelligent coding, and this is the second part. Of course, it's important to encode these areas, or it can be important to encode them with higher quality. But what we could do also simultaneously, we could also think of that what we are encoding and use some intelligent machine vision algorithm for that, so that we can somehow, for example, segment that video or use some content tagging there, so that we can already simultaneously with encoding, we can, for example, find that there are some bags there and include that information already in the bit stream. And at the end of the day, then we could have this kind of a video that it's compressed, maybe also with region of interest coding, but also these tags have been somehow tagged there that okay, now we know that everything goes fine. For example, there could be like if there are some boxes, for example, there, and if one of those boxes is empty, it would be, for example, marked here in red that okay, that there is some problems with that box. It's completely empty. So please check that out. What happened there, and everything is basically recorded in video.
How you can find this?
You can use those same messages there. As SEI messages. So basically you can use those messages there, how you can include this information there in the video. Of course, then another question, more harder question, is that how we can produce the bit stream like this. That there are multiple options for that. I mean, like this, reconstruct this kind of video. There are multiple options for that, and one option is that we use somehow dedicated decoder for that. Of course, then it's not anymore completely compatible with the standard, but that's one option. What we have thought that in specific applications we can be little bit dedicate that decoder part also, so that, for example, some company gets what it wants that way. Yes, please.
How can you use the information that you have? For example, here you have that because this is very precise, and for standard must be very generic. You can have random objects in here. So when you know there are objects moving in the video, for example, how do you use that information in encoding?
Basically, how I see that we have here some kind of real-time machine vision algorithm which detects those objects and informs video encoder that in that area of video encodes that with better quality, and it has to be like real-time operation. Of course, in most cases, what I have discussed with companies, they already know the region of interest beforehand, so it's not a static area. But I don't find it so interesting as a researcher. So somehow I'd like to have there also some kind of dynamic way of changing that regional interest whenever needed. And for that, I think that we could use some machine learning algorithms. I'm not sure whether I was able to answer your question, but if you have any further questions, I may try to answer them, or maybe I can also pass on that question to Alex, or maybe we have to call to Finland or do something else. Okay, let's move on. So far I have only talked about video coding for humans, and I think there is also one very important aspect, and which is all the time gaining more ground, and it's video coding for machines. And I also already heard from Alex that there may be also someone in INSA or someone of you, okay, who are dealing with this one. And this is quite interesting thing, and actually this is quite closely related to the previous slides what I just presented about this region of interest, because again, we are somehow trying to modify that idea that what we'd like to just extract from the video. And this is very new topic to us. And of course, here also we are more interested in the encoding part of that. But then there is also this decoder part. And again, I would see some opportunities for collaboration in this field. And currently we are focusing mostly on this kind of an idea that also the video, what is compressed, is somehow also visible by humans, or somehow also humans can understand the video. But that has been our approach so far. I don't know what you have done here, but is it a similar thing that also humans can understand it, or are they just like a list of features?
There is both approach. In my case, I'm not using features extractor like with neural network or anything. I'm using also similar thing like that, but I'm not using, as you may do, feature extraction to help the video encoding part. So there is multiple approach, but I'm more like looking at how conventional video encoding algorithm manage to encode information, and after that, how just algorithm manage to deal with this compressed content.
Okay.
Do it or not.
Just for curiosity, are you using like VVC, like VTM or something? There.
It's slow, so I'm using a VV
Okay. Yes, yes. But basically VVC based solution.
Exactly.
Yes, yes. Yes, VTM.
Not only I'm also using that. So maybe I can use it if you can the connection.
Yes. I was just about proposing that, but good, Alex. Bring it up. Okay, but this is very new topic to us, and we are very interested in this. And continuing with these ones, because humans are not by far the only ones who are using that video, especially nowadays in the field of autonomous vehicles, for example. There is so much things that intelligent vehicles want to also see. I'm going to talk about that a little bit more later. Okay, that was all about video coding in general. So like video coding for humans, then some region of interest things, and also video coding for machines. Then a few words about video processing, because I'm easily branching a little bit too much with this presentation. So I'm going to just quickly show what we have done also in that field. So stitching. When talking about 360 video, one can quite easily meet some stitching software. And if you happen to be interested, our GitHub site, there you can find a real-time video stitcher, which can be used. And for, I would say, for a HD video at least, you should be able to stitch different videos. But of course, always the question is that what is the platform and what is the resolution? Is it real time or not? But I would say that with those platforms we are using, we are able to stitch like 6 HD videos in real time. And here is one example of that stitcher result from our corridor. And as you can see, it's not very crowded yet because it's times of Corona yet. No, this was actually taken before Corona. Just kidding. And then also post estimation can be interesting area for someone, especially for us. We had one project where we needed this one, so we have also created our own stereo 3D post estimation algorithm. And the point here is that we are not using any depth cameras or anything like that, but just like two different basic cameras and trying to find out the post that way. So no LiDARs or anything like that is used there. And then when talking about this volumetric video thing, which I mentioned, and which was shown there on the right-hand side, when I presented, gave that sneak peek to our things. This Open 3D Gen is something which is also closely related to that thing. And this is about using basic like consumer RGBD cameras for capturing the environment and then generating like a real 3D model of it. So this kind of workflow we have created and published, by the way, one paper about it in IETR conference. But the basic idea is that we just first have to use cameras and capture the environment, and then try to do this also in real time. I would say that most of these steps can already be done in real time, but the last is texture projection is not yet in real time state, but hopefully it will be in the future. And also, last but not least, let's touch on this autonomous vehicles part a little bit. So what we have done here is that we'd like to first use some sensor information, and in our case, we are combining LiDAR and vision data together in order to get some kind of understanding of the depth information also, and being able to create this world better. And then we use view synthesis for that in order to understand different sources of sensors, and that way create some kind of virtualization for some existing physical location in the world. And I'm going to show one video about this so you can understand it better that way. Okay, then the last but not least is the video streaming part. We started to realize that we have to stream video in multiple places, and then we also found out one problem, that there wasn't any good open source library for RTP streaming. So that was the reason that we created it by ourselves. And it's called UVG RTP, and you can find it almost in the same address on our website. And I would say that it's quite complete all nowadays already. So you can find there like RTP and RTCP protocols are supported, and also like VVC support, AVC support, and HCPC support. So all the main standards are supported by this library, and also some security aspects have also been taken into account. So it's quite widely used nowadays. Also, many companies have been very interested in this, because this kind of software you just can't find open source currently, except for this one. Now we have it. Okay, and then about applications. Seems that I have looked at that clock, but it seems that it's not moving. So probably if we'd like to speed up this a little bit, and if we'd like to also give some time for Alex, so it depends, because I think we were requested to have uvg266 presentation, and I have only presented one slide about it. So okay, I will just quickly go through these things, and we can get back to these probably later on. But why we are developing these applications, the main point with this is that, of course, there are many other applications already. You can buy off-the-shelf products, and there are applications. But the reason why we are developing these is that we'd like to also use our techniques in practice, because this is the way we can understand what is wrong with them. And even though everything looks fine in theory, or maybe as a standalone component, everything could work fine. But when we combine them and start using them in real applications, typically we have been able to find like tens or hundreds of different problems there, and that way we have been able to fix them. And then when someone else likes to use them, again, those components are much more reliable. And this is one of those examples that now we are talking about normal video communication, and there are Teams, Zooms, etc. So there is nothing new in that application itself, but this is in that sense quite interesting combination, that here we have combined in this our Quas video call software, we have combined our encoder, our UVG RTP streamer, and also we have used INSA's open HCDC decoder. So this is quite nice combination. Plus also different audio libraries are there also. And another good thing with this one is that if something starts bother us, for example, in Teams, there is possibility when we get this ready, we can also implement those features here ourselves and make it even better for us than the Teams can currently provide. So these are the reasons why we'd like to also develop these kind of quite basic applications. And then about remote monitoring, I think I've already talked about this, but a little bit. But the basic idea with these ones is that we'd like to somehow create this kind of vision pipeline, which is understandable for humans and for machines. So I'm quite interested in this kind of hybrid human vision, human machine video coding. And there can be scenarios in 2D or 360-degree video world. And we have one big national project currently where we are developing these kind of solutions for connected manufacturing. And in that field, you can find these kind of applications that we can have some remote monitoring system where we produce video data which can be seen by humans or by some machine automatically, that we don't need, for example, human in the loop at all. Or there can be situations that 90% can be handled by machine, but then there are some severe exceptional conditions when we need human eye there to see what's wrong with the current production line, for example. And it's also important that we are able to create different bit streams for mobile phones or for like 360 video. So there should be multiple different streams which can be adapted to the different end user terminals. And this is just one example that we can have used this for detecting some problems in, for example, in production line, or we can just detect this single actuator there, what it is doing there, is everything fine. Or we can also use this kind of product quality monitoring here. I already gave this example that, for example, we can detect these boxes, and if there is an empty box, then it's recognized there that, okay, by the way, there is an empty box, please do something with it. And also we can have some worker monitoring there. If some new worker has just started, to make sure that he or she is following all those regulations, for example, needed there. And we can also think that we can also guide him or her how to work there better. So basically, with these kind of systems, if we would be able to get rid of this human eye idea completely and only machines could detect this system, we could do this like 24/7. And one good thing is there that even though humans are present, the same experts can be used, for example, throughout the country, because if you can just remotely connect to those factories, you don't have to travel. And that also saves time, and the same experts can be utilized in multiple different plants. So this kind of hybrid AI-powered techniques for human-machine vision cooperation is of our interest here. But also this kind of idea that also these techniques can be used to think of this kind of video streaming, that if there is, for example, some problems with bandwidth, we can adapt to those diversified bandwidth conditions that way, that we use some machine learning, for example, techniques for that in order to make encoder understand that now you have to compress better, or now you have more bandwidth to use. But just as an example. And then there are different remote piloting issues. This is one of our big Excel projects currently, where we are developing this kind of video streaming solutions for drone monitoring. And also we are developing techniques for to monitor driver and passengers, in order to understand if they are doing something dangerous there, or if they are not anymore focusing on driving, just to alert them. And one important thing here is, because we are video guys, we'd like to do this via video streams, that you don't have to, for example, wear any headsets or anything like that. And there are also different advanced driver applications where we use video. For example, this example here, that we can, if this is the real situation, we'd like to give the driver possibility to see what happens just around his or her car, and virtually give this kind of information. That we have multiple cameras mounted around the car, so that he or she can see what is happening there. And the idea is to provide the driver with this kind of aerial view of the situation. We found that the most relevant solution for that. But it doesn't have to only be driver's own vehicle, but also other vehicles can be made somehow virtually visible. And for that, we have created this kind of new technique, that if this is the real situation, then there is possibility that first we have to be able to detect this vehicle, of course, and then we can make it like transparent at least partly. But of course, this requires that there are cameras in the car in front, for example, and then we have to also like transmit that video data and do view synthesis, etc. So there are multiple steps, but we have been able to create this kind of system in virtual world already. But of course, there is still a long way to go before we can think it's in real world. And I have talked quite a lot about different autonomous vehicles, etc. But because if you go outside and start thinking of different technologies or how I could integrate that into my car, and then we set up cameras there, it takes time and it's quite hard because we don't have permissions, for example, to do those tests for in normal roads, etc. So that's why we realized like 5 years ago that we have to start creating our own virtual environment. And we had our first version of it. We took one existing vintage city from on the internet and used that. But then we realized at some point that we cannot use it because it's not realistic enough. The roads were too narrow that you cannot drive there as a normal car, or those street corners were too steep, or something like that. That it wasn't possible to use that. So that's why we made a decision that we started to create our own virtual environment. And because we live in Finland, Tampere, and the precise area is called Hervanta, we thought that why can't we just model our own area there, this campus area. And that was the main motivation why we started to do this one. And actually this environment is currently quite comprehensive already, and we try to make it as photorealistic as possible and also lightweight in a way that you can still basically perform different application validations there. For example, we can use this for our driver in the loop simulations where driver is driving in the city, and that way we are able to detect those drivers' emotions, for example. Or because it's real time, also different this kind of that we can have some software or hardware block there, which is part of the system, and we just test how well it works in a virtual world. And also this virtual world is very important if we think that we'd like to collect some data for some neural networks. And as long as the environment is realistic enough, we can also use that for this kind of training if we are not able to get the data, like physical data, somewhere. And also this kind of visualization of different transportation planning and traffic control flow schemes are possible here. So before I end this meeting, I could this presentation, I could also give you a few. Alex, could you, by the way, play them? Play a few videos. They won't take more than 5 minutes altogether. So then I'm done.
Oh, which one first?
Let's start
with,
yes, let's start with that. Yes, Hervant.
So here, oh, wait, because I touched something, of course, everything's spoken.
For some reason.
You can detect the il détecte pas d'écran. Yes. Thanks. Ah. Okay.
Okay, now it works.
Yes. Am I sharing my screen now? Not a good one. Okay, good. Up and start from the beginning.
So this first video is about this Hervanta environment. And now you can see it. And it's up to you whether you think it's realistic or not. But at least this is realistic in Finland. There's lots of rain and snow you can see there. But here is, by the way, our new tram line. Unfortunately, the tram itself is still missing in our virtual world, but in physical world you can find it. But the basic idea here is that the whole environment is modeled as realistically as possible in order to be able to visualize and test and validate different technologies there. So there are lots of features which may not be so interesting when, for example, you are, driving your car somewhere. But for example, with drones, if you think that you are flying a drone here and you can see inside those buildings, it may be important in some cases, and also different lighting conditions, for example, and also dawn and sunrise, sunset, and nighttime, and also cars are light on in those cases, and different weather conditions, for example, heavy rain. People seem to be quite happy about it still, without umbrellas. And also this is very typical in Finland. Winter conditions. Of course, those car models are not very precise yet. It means that those different dynamics and those things haven't been considered yet. But that's also one thing what we are going to do in the future, hopefully. Okay, that was all about it, about this environment. But then I'd like to, I think we can just take this inter part. I think it's enough. And when I was talking about this kind of view synthesis issues, how we can make other vehicles transparent. So this is just an example. And here we are using still our old virtual environment. So this is not relevant yet. But as you can see, that making those cars invisible can be useful. And this whole technique has been created here in a way that we could use in principle similar techniques also in the physical world. So we haven't created this like that. We just make it transparent using some of the virtual tricks here. Of course, it needs that we have to have very accurate lidars and also very accurate positioning of the car. But basically, this technique could be replicated also in real world. And here you can see very illustrated example of why we'd like to do it. And when you have this system on, you can detect the car and you don't bypass the track before. It's more safe.
So which camera would see the taxi?
Excuse me?
Which camera would see the taxi? Not the
Yes. This is one of those biggest concerns there. But of course, the truck has to have the.
Okay.
The idea is like every car have a camera on it, and all of the data can be transmitted everywhere. Then we are able to provide this kind of solutions where we are using the video data from the truck here that will give us this visual information.
So we are addressing future, not current situation. But actually, there are already quite many cameras in the vehicle. So basically, even in the near future, some kind of experiments like this could be possible. But of course, I wouldn't expect this to be reality in this decade at least. Okay, I think that was all, and sorry for taking 1 hour already for that. So what shall we do with this UVG266 part? So
I think in 15 minutes, 10-15 minutes can be done. So if it's okay, I can just start. Right away. Okay, so I forgot to put my name on the slide, but I guess that most of you My name is Alexandre Mercat. I was a student
On n'a
here.
pas les slides.
Okay. Thanks. Yes. Ok. Partager. Hop. Can you see the slide now?
C'est bon?
Excellent. So, yes, was it working? Next. Perfect. So, yeah, just to introduce myself, my name is Alexandre. I was a student here for my master's degree, then I was a PhD student here. And now, since 2018, I'm working as a postdoctoral researcher in the Ultra Video group with Jarno. Today, I will just quickly present you this seminar that is titled From HVC to VVC, the first development steps of our new uvg266 encoder. So the context, just quickly, I put this sentence here. Did you know that according to Cisco, global IP video traffic will increase fourfold from 2017 and account for 82% of all IP traffic by 2020? I put that here because it's the same number that we can find in all video compression paper for about 10 years. And this year it starts to be outdated because now we are not in this kind of prediction. So that's the idea here is still the same. We are living in a world where video is used everywhere and always more and more. So we still need to compress this video. And it's why 2 years ago, they standardized the new video compression standard named VVC that is able to have the bitrate of for the same visual quality than HVC, its predecessor. About the introduction of this work, so as Jarno just learned before, we developed Quasar, our own practical HVC encoder since 2012, and it was Graph Times awarded. So this current encoder is relatively mature, and most of the issue was solved. So it's now a really, really good HVC encoder. And at the same time, this new standard just appeared 2 years ago, and when we were looking the both HVC standards and knowing all of the similarities between both, we decided that Quasar seems to be a really good base to start to implement a new encoder. So then, in 2018, we started to develop a new encoder named uvg266, that it's a VVC encoder that is based on Quasar. So what it means that they are sharing most of the structure, and indeed all of the improvement that we are able to do in Quasar and uvg266 can be merged together because they are sharing the same Git repository. History. So about the scientific approach of our work, probably most of you know about VTM, it's a VVC reference software. So to develop the new video codec, the GVET working group was working on this reference software that includes all of the VVC tools, of course, and so achieve the best encoding performances. But this encoder is only slightly optimized, or not really, and don't have any thread parallelisms. So it's for that not really a good base for a practical encoder. However, currently, if we're looking, for example, the VVN encoder, that is the other practical encoder that is currently available, they decide to try to create a practical encoder based on this VTM encoder. If we're looking for HVC, it's the same thing that have done X265. They try to develop their own practical encoder based on of HM. It's a way to try to do that. So the good part of this approach is that you already have all of the VVC tools, so the performances of your encoder will be really good, but it's really hard to try to speed up the encoder and be able to reach real-time performances. On the other hand, we have our own practical HVC encoder that, as I said before, it's quite mature, and in order to reach real-time performances, it includes high parallelisms at data level, thread level, and also process level if you want. So we decided to try to take this opposite approach, that we're not starting from a VVC encoder to try to speed up the reference encoder, but we are trying to start from already really, really fast and performance encoder from HVC, and we are trying to upgrade this HVC encoder to VVC. So for that, it's interesting, and we are, to the best of our knowledge, we are the only one that's currently doing that, at least in the open world. So this is the overview of the development flow of this upgrade from Quasar to uvg266. So it was quite easy. First, the idea in 2018 was trying to convert the HVC encoder into a VVC encoder. So we was focusing on the KBAC. So for each HVC tool, we have to change the KBAC context and bits, and then try to see if when we are running this new tools and we try to decode, we are able to get the bit stream. And if we have some error, we have to fix this error and just start again until we don't have any error anymore, and we can just start to do that for a new HVC. After this first phase, when we start to implement the VVC tools, it's the same flow where we just then now implement a new tool, VVC tools, and then add the kind of context and bits. And once again, try to fix all of the errors. And when we don't have error anymore, it means that we are able to integrate these new VVC tools at the encoder. So then about the uvg266 optimizations, as I said, like VVC structure share like a big part with HVC structure, except for the MTT and chroma separatory. So from that, we was able to, in our first phase of VVC encoder, to reuse most of the HVC tools. So we already have an encoder that was encoding VVC bitstream and with the HVC tools that was available. And with that approach, we were able to use around 80% of the low-level optimization that we have developed for many years now in Quasar. So in details here, you have different functions in Quasar and the reused low-level optimization. So at least from that work, we want to show that, okay, if one company or any teams have already an HVC encoder, then using to create a VVC encoder, then you are already able to reuse all of the work that you spent on HVC. Same things about parallelisms, for example. Here, this is the BTD parallelisms of HVC. So in Quasar, we was able to encode each row in parallel according to the dependencies. And when they changed this process for VVC, when they removed some dependencies, it was really easy for us to just update these dependencies in the encoder and then have already some PET parallelisms available in our VVC encoder. The current status of uvg266, so which are the supported tools? We are focusing so far on intra tools as the first time. So we already support all HVC tools, but also multi-transform selections, matrix interpolations, multi-reference lines, joint coding and chroma residual, cross-component linear model, Luma mapping with chroma scaling, and adaptive loop filter. So then, from this specific approach for us, what is interesting to see is to be able to quantify, compared to VVC encoder that support only HVC tools, what are the gain and what is the cost in encoding speed of each of these VVC tools to then be able to build like a VVC encoder that will be able to maximize the encoding performances according to the complexity limitations. So here we were able to quantify, compared to VVC encoder that support only HVC tools, what are the gain and the cost of all of these new VVC tools. And then these kind of informations are really interesting because if, for example, some companies also want to do the same process, from that kind of result, they can select, they can know, okay, these tools is just like a cost, a lot of complexity, and will be really hard to speed up. So then we can just decide that it's not the more interesting tools that they want to implement, and then maybe focus on the most relevant one. So from that, it's quite interesting. So to conclude about the future works, we have a lot of work still, but uvg266 works already in OINTRA. So about the future works, we continue to implement new tools. And then later we are going to add, currently we support only quad-3 tunings that was already included in HVC. And now we start to think about how we can include these new entity partitionings and comma separate tree that are like a big change in the encoding process. But the data structure of the encoder can be reused, and we already have this kind of rectangular blocks in HVC also for intercoding. So the idea now is just to reuse all of these blocks that we already have in the encoder and to put it in a way that we can support this new partition. We have also some works to fix tools for interslices to then be able to have like also first versions of the intercoding of uvg266. And then after that, we are going to work on the preset regenerations to be able to propose some presets of coding parameter for people according to the complexity and from ultra fast to reverse. Of course, other work that we have to work on it's some video improvement of algorithms of old and new tools. For example, why not trying to apply the works of some really good PhD students and some accelerations of VVC and try to see what we can achieve in a practical encoder. And also, we are going to work on the technical support. Thanks. If you have any questions, feel free to contact us. It's easy to send an email on Slack, and just now you can still discuss today afternoon, tomorrow, and then I'm going to come back sometimes. So, there. Here it's encoding speed, so it's slower. So yeah. So what we can see here, it's like the debugging thing, the log just improved the encoding efficiency for quite free, but the ALF, for example, costs like a lot of complexity. Yeah. Yes.
We have one period prediction.
We have some of them, I think. Yes, and no, I think yeah, we support. We support. Yes. I'm not sure. I have to ask. No. Yeah. Okay. So yes. So the yeah. We already published one journal paper about uvg266 on transaction and consumer electronics. So feel free to look at this paper if you're interested.
And we have created quite comprehensive complexity evaluations about those tools in order to understand, before starting to implement anything, we first understand how much does it cost and what is the gain it gives. And this kind of.
This paper is under review, but we hope that we will be soon. And yes, yeah.
What is
good questions. The last results I don't know because people are always working on that and improving tools. But in the publications we report. I think we are 2 times slower, and we are able to save something like 10% of the rate, maybe, if I remember right. The baseline, like when we have a VVC encoder that only includes HVC tools, then the speed is quite the same, but we have some degradation of the rate. But when we start to enable some tools, then we are able to be better than Quasar. And now, and compared to VVEnc and VTM, we are faster. But we are 20% behind in terms of video rates. It depends on the configuration. I don't remember which one we profiled at that time because it was 1 year and a half ago, 1 year ago. But yeah, we will always still behind for our ongoing performances before that we are able to support all tools. But
of course, we are faster than.
But we are already faster, and the idea it's really that it's to see what happens when we are going to use this approach that we start from at HVC encoder and we try to build a VVC encoder. And for us, we are thinking that it's quite interesting research also for publications, just because like many young companies have their own VVC encoder, and at some point if they want to develop their VVC, then they have different approach, and they can start from scratch. They can start from VGM, they can start from as well, or they can already start from when they have in HVC and try to prevent them. So,
but when thinking of this comparison at this very moment, we are talking about like first person versus fine-tuned HVC encoder. So this is not in that sense yet fair, but of course, if at the end of the day we are not able to get better performance and the complexity will be much higher, we conclude that we don't need VVC anywhere. So, but I strongly believe that we are going to beat quite nicely Quasar. Of course, it will be more complex, but still the PD rate would be much better.
thanks.
The good news for all of you is that if you like to communicate with us, you can also communicate in French, so it's not a problem. But then it's up to Alex how well you are able to translate everything in Finnish.
Morista. Yeah, in Finnish, let's see in 10 years. Let's hope.
You can still have a demo for Ultra.
Oh, yeah, we could try to build a glass-to-glass demo or end-to-end demo of intra-coding with VVC intra-coding from uvg266 to OpenVVC.
Using UVG RTP in between. That would be nice.
Yeah, it's currently it was one of the first tasks for Guillaume, just trying to create a CMake that we can compile OpenVVC in Windows environment, because and then to try to make this full flow between both solutions. So definitely we're going to try to see.